Hello everybody. So I've already made several different videos regarding different ways that you can calculate a limit, and there's many different ways it can be done. But as far as you getting a random problem on a quiz or a test or an assignment or whatever, there is some deciding that might have to happen as far as how you should go about it. Right? So what I wanted to do was talk about a flowchart approach to deciding how a limit should be done. Okay? So let's say our goal is to calculate some limit. The limit is x goes to some number a for some function f of x. So here's the flowchart. We'll talk through it and then I'll show you a few examples. Do the instructions in the question mention a specific method, such as a table or a graph? Because you can calculate limits with tables and graphs. That's one possibility. If yes, then use that method. That part's pretty simple. All right, just follow the instructions. What if it doesn't mention anything specific like that? Okay, here's our next question. When you plug in this number a into that function, does it give you 0 over 0? Okay, if it doesn't, then whatever you get when you plug that number in is probably your answer. Now, I say probably because although in our assignments it's always going to be the answer, it will be the answer, it is possible that somebody could create a really unique problem that defied this. All right, so but let's just say that if you plug in the number a and you don't get 0 over 0, whatever you do get is going to be your answer. What if when you plug in that number a that your limit's at, you do get 0 over 0? Okay, well here's what happens then. You simplify the function, and there are different ways to do that, but I'll show you some examples. Then you let the x be a. And what you get at that point will probably be your answer. Okay, again with the word probably, but if you do everything the right way and you're familiar with the type of examples that you'll see, then it will work out for you. Okay, so let's look at some examples. So here's an example, and it says use a calculator to estimate the limit. Now, use a calculator, those are instructions on how you're supposed to do this. That means when you see use a calculator, that means to make a table, okay? Another way that might be expressed is to calculate the limit numerically. Okay, so you may say instructions that say use a table to estimate the limit, or the instructions may say use a calculator to estimate the limit. The instructions may say estimate the limit numerically. All of those mean the same thing, and that's make a table. So here, this is the limit as x goes to -1, okay, for that complicated looking function. All right, so well, all right, here's the way a table would look. Right here, here's a series of numbers where the x is going to -1 progressively from both sides. Notice all the decimal places. Limits are on a, you could think on a microscopic scale. So if I was going to go to -1, I would want to do something like this. -1.001. Then I'll go a little closer. -1.0001. And then I'll go a little closer than that, and so on. From both sides. Here's going to -1 from the left. Here's going to -1 from the right. Okay, left, right. And does that force some, collision over here? So I plug these numbers into this function and I get these answers, but are those answers closing in and like they're going to meet in the middle? It doesn't look like it, because as far as my x's on the left go, it's like sending up bigger and bigger negative numbers up to -599,999. But then on the other side, the numbers on the left-hand side, or the right-hand side, it's pushing to 59,000. So like this progression is not going to meet this progression somewhere in the middle. They're not headed to the same place, okay? If this limit had an answer, then right in here, where the left is supposed to meet the right, we would see some agreement. And we don't. So the answer to this one is does not exist. All right, so we did this limit by table, as it said. Our conclusion, though, was that the limit doesn't exist. here's another one. It says use a calculator to estimate the limit. Same thing, that means make a table. So I made a table, and this time the limit is x goes to 1. So here you see that I'm approaching 1 from the left as we think of the number line. I mean, I say left and right, but here's 1, and then like 0.9 is left, and then 1.1 is on the right. Okay, so here's going to 1 from the left, here's going to 1 from the right. All right, I take those numbers, put them into my function, and I see if there's some agreement in the middle. Does it look like it's going to the same place? Yeah, I'm pushing close to 1. You know, 0.999987, that's pretty close to 1, as the x goes to 1 on the left. And then on the other side, 1.000000125, that's also pretty close to 1. So here, it does appear like as the x's get close to 1 from either side, it forces the y to also get close to some specific number, which is also 1. All right, so our limit is 1 this time. Okay, so that's the table method. If it says to make a table, make a table. All right. What about this one? Evaluate the limit. Now, back to my flowchart. Do the instructions mention a specific method? I don't see any specific method mentioned here. It just says to evaluate the limit. So what did the flowchart say? No specific method mentioned. What happens when you plug in the limiting number? X goes to A. Plug A in. Do you get 0 over 0? So I plugged 4 in to this function like that, and I got negative 12 over negative 3, which is 4. That's our answer, right? Because that's what the flowchart said. Plugging in A did not give 0 over 0, so all right, whatever you got when you plugged in A, that's your answer. So let's say here's our answer 4, simple as that. Okay. If you're somebody that likes to confirm and check things and make sure you're right, I bet if you put in 3.999 or 4.001, kind of like in our tables, you'd get some result very close to 4. It'd be confirmation of that. All right, what about this one? Evaluate the limit. Again, no specific instructions, okay? All right, let's plug in that limiting number and see if we get 0 over 0 or not. So this says the limit is t goes to 15, the variable is t. So I plugged in 15, and I did get 0 over 0 when I did the calculations, okay? So the flowchart says, all right, in that case, we need to simplify that original function. Then, after you're done, let the variable be the limiting number. So, okay, how you simplify and how you reduce varies from the questions, okay? So when I have something that's factorable, the reducing will be in terms of factor and then cancel. All right, and so we'd have to go into this knowing that, well, this thing right here, like t squared plus 3t minus 270, that's the kind of thing that can be factored. And t squared minus 225, that is also the kind of thing that can be factored. The way that I factored this, because different things are factored different ways, is I find two numbers that simultaneously can add to, or sorry, I messed that up. Okay, I find two numbers that can simultaneously multiply to negative 270 but add to 3. That's the technique for factoring this sort of thing. So I made a little factor tree of 270, somewhat based on trial and error, and I saw that 270 can be 15 times 18. So 15 times 18, that could multiply to 270, but it could add to 3 if you made it negative 15 times positive 18. That would multiply to negative 270, would add to 3. So that gives you your factorization, t plus 18, t minus 15. All right, so that's how you factor that sort of thing. This down here, t squared minus 225, is called a difference of squares, a squared minus b squared. This is t squared minus 15 squared. 225 is a perfect square. It's 15 squared. So I see it like this. A squared minus b squared factors as a plus b times a minus b. So t squared minus 225, t squared minus 15 squared will be t plus 15 times t minus 15. Okay, so I factored it in the top factors one way, according to one criteria, and the bottom factors another way. But they both factor. And then look, they both have this common factor that can be canceled. And I'm left with t plus 18 over t plus 15. Now it's reduced. Okay, so the flow chart said we got 0 over 0. Simplify it, reduce it, then plug in that limiting number. Okay, so I got this. Now our limit was for the variable to go to 15. So if I plug in 15, it should work. It should give me my answer at this point. I let t be 15, plug it into this thing right here. I get 33 over 30, reduced to 11 over 10. That's our limit, okay? So our limit this time is 11 over 10. But we did it by the flow chart, right? Okay, and also we have to know how to reduce this kind of thing. But let's look at one more, because this factoring and canceling, this reducing that has to be done if you get 0 over 0, it might be different in another problem. Okay, what if we had something that wasn't of a factorable form like this? Okay, so that would be like this one. Evaluate this limit. Now again, I'm going to stick to the flow chart. Flow chart said that, well, if you plug in your number, you get 0 over 0. You need to reduce the function you have and then try plugging in again. So let's see, I plug in 5. This is the limit as x goes to 5. I plug that in, I do get 0 over 0. Now, the way that you reduce this is you multiply by this thing called the conjugate. If your original function gives you 0 over 0 and it's made of square roots, then the way that we reduce it is by multiplying by the conjugate. The conjugate is what you would get if you look at the portion of this that's made of square roots and you change the sign in the middle. So the conjugate of root x minus root 5 is root x plus root 5. But I have to multiply by 1. So the conjugate turns out to be the thing that simplifies the roots away. But think if I took this and I multiplied it by a number that wasn't 1, it would be a different number, right? Say I take whatever I have and I multiplied it by 2. It's not going to be the same number I started with. That's the way math works. But if I take the conjugate and I put it over itself, what is that? That's 1. And then multiplying by 1, it's not going to change anything. I got my problem that I'm working on. I multiply it by 1. It's not going to make it some different number. It might make it look different, but it will be the same number. Can numbers look different and be the same? Yeah, I mean, 4 is the same thing as 8 over 2. I mean, those don't look the same, but they're the same number. It's kind of like that. All right, anyway, so I multiplied the tops together. I use FOIL multiplication, which you're looking at right there. The bottom parts, I'll just write them next to each other. This multiplied by this. Okay, that's what you see here. I noticed that the conjugate, once you multiply them, the middle parts do cancel, okay? And you're left, that's what the conjugate does. That's why we introduced it, and it's the whole trick to simplifying this. You're left with x, take away 5. X, take away 5. But on the bottom, you got x take away 5 times root x plus root 5. So you're left with this. Okay, now it's reduced at that point. So, according to the flow chart, we reduced it. We should be able to determine our limit by now letting x be 5. Okay, so I take this reduced form, I let x be 5, I get 1 over root 5 plus root 5. That's an apple and an apple, so it's 1 over 2 root 5. An apple and an apple is 2 apples, so root 5 plus root 5 is 2 root 5. That's our limit, okay? All right, so let's make our answer official. Include that. Okay, there we go. And then we're done. Okay, so that's a little bit of everything for the flow chart. You can trust the flow chart. It's dependable for the assignments that we have. The only catch with it is that with these 0 over 0 cases, that you know that reducing is necessary, But how we might reduce by factoring is different than how we would reduce with the conjugate. But outside of that, we'll get the same result in the same process.